Hello and welcome to another tutorial on data analysis fundamentals brought to you by Earth Creations. This is lesson 12 where we walk you through the analysis of covariance called Ancova, and we will be seeing a number of assumptions. In lesson 11 we saw the analysis of variance, Ancova. In lesson 10, we saw the independent sample t-test, and in lesson 9, we saw the dependent sample t-test. We hope that you are following along. Ancova stands for analysis of covariance. It is a statistical test similar to ANOVA, but in which there is an additional continuous independent variable called a covariate. Whereas Ancova looks for differences in group means, Ancova looks for differences in adjusted means, that is, adjusted for the covariate. When to use Ancova? As earlier mentioned, there are a number of assumptions that should be met when running the analysis of covariance. Again, do not worry if one or two of these assumptions are not met. It's common to see that in real-world data rather than to see in textbook data, which has everything perfectly done. However, there are some assumptions that must be met for you to run the analysis of covariance. So the very first assumption is that the dependent variable and covariate must be continuous. The independent variable should consist of two or more categorical independent groups. The third assumption is that there should be independence of observations. And the fourth says the residuals should be approximately normally distributed for each category of the independent variable. The data should not contain any significant outliers. Here we talk of significant outliers because you could have some outliers which do not affect your result. There should be homogeneity of variances, which we will see in SPSS using the Levene's test. The covariate should be linearly related to the dependent variable at each level of the independent variable. There is need for homoscedasticity, and there is need for homogeneity of regression slopes. This last assumption is one of the assumptions that must be met. There are two types of Ancova. We have the one-way Ancova where there is one independent covariate, and we have the two-way Ancova where there are two independent covariates. Demonstrate the analysis of covariance. We have a data set containing the number of times pregnant women took Fansidar. Here, that is going to be our independent variable. And we have another variable which contains the birth weight of their babies measured in kilograms. That is going to be our dependent variable. In the last tutorial, we saw how to run an ANOVA using the tool. However, in this data set, there are slight modifications on our independent variable. We have just two groups: those who took Fansidar less than 3 times and those who took Fansidar 3 or more times. And we think that not only Fansidar alone affected the baby's weight, but the gestational age as well. The more the baby remains in the uterus, the more the baby grows. So we will be using gestational age as a covariate to run the analysis of covariance in SPSS. Let us see that. Here we have our data set, which contains up to 150 samples, which is good. And then we will check for the assumptions. one after the other. So the very first assumption is that the dependent variable and covariate must be continuous. Because you can see that here, the dependent variable birth weight in kilograms and the gestational age measured in weeks, they are both continuous variables measured at the scale level. Okay, the second assumption is that the independent variable should consist of two or more categorical independent groups. Here we have just two groups. The first group took fancy less than 3 times, and the second group took fancy 3 or more times. And of course, the groups are independent. You could not take fancy less than 3 times and then you took it again 3 or more times. So the groups are independent, and we will check if the dependence variable contains some outliers. To do that, we come over to analyze, descriptive statistics, explore. Then we send our dependent variable, the dependent list, go to statistics, check outliers, click on continue, come to plots, and we will not want stem and leaf, but we want a histogram and normality plots with tests. Continue, then we click on OK. And here we have our data, and the Shapiro-Wilk test of normality is telling us that our data is not normally distributed. Because we have significance here. But looking at the histogram, we see that the data is fairly normal, fairly bear-shaped. And the analysis of covariance is robust to normality. So we will continue despite what the Shapiro-Wilk is telling us. And the scatter plot, or rather the box plot, tells us that there are no outliers. We might also want to check for the covariance, if it is normally distributed or not. So we come here and we just check for the covariance. I think the Shapiro-Wilk will still tell us that it is not normally distributed, which can be seen here. It's fairly not quite bear-shaped. And the scatter plot, box plot. Box plot tells us that there is an outlier down here, but we want to know if the outlier can affect our results. So we compare the mean with the 5% trimmed mean. The mean is 39.66. 5% trimmed mean is 39.7. So there's no big difference between the mean and the 5% trimmed mean. So that outlier wouldn't affect our result. So we will continue with the other tests, the assumptions. Homogeneity of variance. We will see that when running the Ancova itself. Then we have the next assumption. The covariance should be linearly related to the dependent variable at each level of the independent variable. So to check for that assumption, we will come to graphs, legacy dialogues, scatter, matrix scatter, define. We send all the continuous variables to the matrix variables and the fixed variable to the rows. And we click on continue. And here we're interested in the independent variable and the covariance. So we have the independent variable here, the right, and the covariance down here, bottom right. So we expect to see a linear relationship from bottom left to top right, but we don't see that here. So the assumption is fairly not met. However, we will continue with the other assumptions. The next assumption is the assumption of homoscedasticity. So we will come to analyze regression, linear. The dependent variable is weight in kilograms, and independent variable, well, we can just put in a fixed factor. The statistics, nothing. Plots, yes, we're plotting our residuals against our predicted values. So Z receipt against Z predict, and one normal probability plot. New, okay. So here we have the almighty scatter plot that I was talking about, I had earlier mentioned. So it kind of looks like a gun, a shotgun blast scattered. There's no actually a linear or a mountainous way of presentation, so it's just scatters around. So we can say that our data is homoscedastic. That's good. So the last assumption, which is very important, is the assumption of homogeneity of regression slopes. It's similar to the Ancova itself. So we come to analyze general linear model univariate. Our dependent variable is weight in kilograms, and the independence or the fixed factor will be our consider. The covariance come down here. For the model, we'll rather go to custom. Take consider to model, we take gestational age to model, and we want an interaction between the two. So we hold the control key or the command key. If you are on a Mac, you highlight both and send to the model. Click on continue and okay. So we have to focus on the table of tests or between subjects effects, and we really want to look at this interaction between the consider and the stationary age, and to see if it is not significant. Good, it is not significant. So we've met the assumption of homogeneity of regression slopes. And what does this tell us anyway? This tells us that the relationship between the outcome, that is our dependent variable, in this case birth weight in kilograms, and the covariance, which is the stationary age in weeks, differs across the consider groups. The relationship between the dependent variable, let me correct that, the relationship between the outcome, that is our dependent variable, and the covariance, in this case the stationary age in weeks, does not, yes, this non-significance means the relationship between the two does not differ across the groups. Which groups? The consider groups. That is what this non-significant means, and that meets our assumption of homogeneity. Variance does not differ. If there was a significance here, we will say that the relationship between the dependent variable and the covariance differs across the groups, and that will mean that our model is inaccurate. So here it does not differ. So we can move over to testing for Ancova. So we'll come to analyze general linear model univariate, and since we had done that for the homogeneity of regression slopes, we will just change the model. In this case, we want to use factorial, continue. Remember, we are controlling for the covariance because we believe that it affects the birth weight as well. So we go to options, and we want descriptive statistics, estimate of effect size, and the homogeneity of variances. The Leve's test, remember we had not tested for it. So continue, okay, and we have that here. Leve's test for equality, it is not significant, which means there is homogeneity of variances. So that's good. So we come down to the test of between subjects effects, and we'll focus on the ancillary group, and here is not significant. So even though we've controlled for the covariance, yet we do not have significance. So what does this even mean to us? 0.48 means there is a 48% chance that the difference between the groups, the faster groups, actually happens due to random error. Yeah, 48% chance is a huge percentage. So it is not unusual for us not to have significance, of course. And what does this partial eta squared mean? 0.003. What does it mean to us? It means that the two consider groups explain only 0.3% of the variance in the dependent variable. That's quite small, right? So even though we control for the covariance, yet we do not have significance. Well, if we do not control for the covariance, I think we will even have a higher percentage here. Let us check that. So we can go back and we say, okay, covariance, we don't want you. Okay. You see, we have 0.84 compared to 0.48. So you see that the covariates actually have an effect, even though overall there is no significance. Well, I hope and believe, pray that you have significance in your own data set. Thank you for having followed this video through. Remember to like our videos and subscribe to our channel. Thank you. See you in the next lesson.